All right. So, Soraya, can you hear me? Okay. We got Soraya in his house. Okay, pH range is the range of pH values over which a buffer system works effectively. Yes, Judah.
I'm sorry. The first two videos, there's days of this aren't up. Is that because you did on the iPad?
Probably. I don't know. I can look for them. Yeah, that they were done on the iPad, so they're probably not really in existence. You could go to my YouTube channel and find them from previous years, though, I guarantee that. All right, so it's best to choose an acid with a pKa close to the pH of the buffer you want. I don't know what that says because I'm walking away. It says, that was close. It's best to choose an acid with a pKa close to the desired pH. The range of buffer is generally within plus -1 of the pKa. What would be the buffer range for an acid if its Ka is 7.1 times 10 to the -4? It's not that. Nope. Someone type that in. Do you see how it says this? A pKa. What does P mean? Negative log. So if we take negative log of 7.1 times 10 to the -4, we get 3.15. All right, so that's the pKa, which means our pH range that this would be effective is around 2.15 to 4.15. Where do those numbers come from? Plus or minus 1 of the pKa. It would work, it just would be less effective, is essentially what they're saying. So the way you would ever see this, and this is just a nugget, there's not a ton of information here that will be tested, but it would give you, it'd say, scientists want to maintain a pH of around 3 for whatever experiment or whatever, something obviously more eloquent than that. And then they would say which acid and conjugate base would be the best. And so it'd be A, B, C, D, whatever. And it would give you the acid. So I'm going to make these up, but it'd be like HF, and then it would give the Ka equal to a number. It'd give HCN with the Ka equal to a number and a couple more. And the way you would do this, you would take the negative log of each one and the closest one. So let's say we did it for here and it came to be 3.03. This one was 3.89. This one was 1.6 and this was 5.2. You would choose that one because the problem said you want to maintain it at a pH of 3. They're not real common, but they are something we should at least explain. Okay, so ask about which acid to choose for the pH range, take the negative P or negative log and see what you get. Go ahead. Go ahead. You can borrow that one. Okay, questions about that? It's like a little subsection of notes that you might forget, but it's going to probably be on your test. All right. Well, this is just another buffer practice. Do you want to do it?
Sure.
Okay, fire away. I'm going to pause this recording. Misha, you're going to make. Thank you. That was with my knuckles too. Who would have known? 20 grams of NaF. How many moles is that?
Oh, wait, no,
That's okay. What's that?
about
No, it's got to be around half. And that's F minus. Okay, then we have 0.5 times 2, so 0.05 times 2 equals 0.1 moles of H plus. So how much acid am I going to make? I guess I should just leave that there. I'm going to write right here, but that's not part of this problem. Okay. All right. So I have how much acid? 0.1 mole of HF. That's my acid. How many moles of F minus then? Okay, then we just Henderson-Hasselbalch that, right? All right, so the negative log of 3.5 times 10 to the negative 4 plus the log of the base, which is this one, over the acid, which is that one, equals what number? 4.03?
Hey, there's always the, what is it called? Probably something error. Called human error? No,
It's called percent error.
Percent error, but there's always the range.
Oh, yeah,
What is that thing called?
I can't remember. Okay, so we had 4.03 originally. No, Grace? Yep, you take your excess, or you take your bigger number and subtract your smaller number from it. It's the difference between the two numbers. So the acid is always equal to the smaller value. Whatever's left over, it's the difference is what is your conjugate. Okay, so now I have this section here. What is the pH after the addition of 20 milliliters of 1 molar HCl? So the pH better go down, right? Okay. All right, so I'm adding 0.02 times 1. I add 0.02 moles of acid, which means I subtract 0.02 moles of conjugate base. So I still have the negative log of that. And once again, this is for this problem, even though I'm writing right here. Plus the log, the base went down. I didn't keep it. What was it? So 0.356. And this one went up to 0.12. Okay, we plug that in. Does that fit with our logic? Yeah. We added acid, so the pH went down, but it didn't go down very much, which is perfect because it's a buffered solution. Okay, so far okay? Yeah, Judah? Okay. Then this is the same situation, but now I've added base. So I'm going to just erase this piece right here. The addition of 30 milliliters of 1 molar. So that's an addition of plus 0.03 base, which means the acid goes down that much, right? All right, so the base of 0.396, right? 0.406. Okay, you're right. That was stupid math. And down here would be he is a bad A. No, I'm a mad fat A. Well, I just do it to try and stay humble because I know it's not true.
What could the F stand for? I'm pretty sure.
Francine or fluorine. All right,
The F minus.
good enough. Oh, what was the answer? Okay. You have to be able to do this on the test. You have to. Maybe if we have time. Yeah, got a non-real answer? What?
Yeah, I don't know. Unless it just cuts something off. Oh, but I was gonna ask earlier. So we keep saying, oh, this is David.
The Henderson Hasselback.
So do one where it's a different type of math.
In chapter 16, we did a ton, which was the different type of math. But in chapter 17, we do a buffer. We're going to always put it in the Henderson Hasselback. It depends. The answer to that question is actually no, because you're expected to know chapter 16 as well. All right, we don't need that anymore. Oh, titration. Yeah, I did forget about that part. Okay, titration was in chapter 4 already. It was very brief, and this isn't that long either. Titration is when you take a known concentration of base or acid and slowly add it to a solution of acid or base to figure out the concentration of an unknown acid or base. Yeah, yep, exactly. The only thing that we're going to do different here is we're going to calculate pH more often. Instead of just finding the concentrations like we did in chapter 4, we're going to take that one step farther and then find the pH. They're really not that bad. So you may, I don't know, I demonstrate one. Have a burette, which we slowly add stuff in. We keep track of the volume of the stuff as it goes down until this changes from some color. We'll say it's blue, but then I add it until it turns green. I'm like, hey, it's neutral. And once I've turned a solution neutral, there's a really cool thing about it. When the solution's neutral, the concentration of H plus is equal to the concentration of OH minus. So even if I didn't know one, but I can find the other, then I know both. I find the other by measuring how much acid I had to add to make this go neutral. And I do math to figure out the moles that it had to neutralize. There's more. Okay, a pH meter or indicators are used to determine when the solution has reached the equivalence point. The equivalence point is what it sounds like. It's when things are equal. That would be the amount of H plus and OH minus. All right. So, or at which the stoichiometric amount of acid equals that of the base. So what we have some sort of indicator here. This is a warm color. So I don't know, I'd assume it was an acid. This is yellow. I don't know why this is pointing from here to there because it's not that. That would probably be an acid as well. It's just showing you different indicators. We would know what indicator we added, and we would know what pH it changed color, like it would be on the bottle or written in the problem. And then we could figure out from there what we have. So the math is essentially like this. So you would have 3 things that you know, and they're given to you in the problem. So let's see, that was probably a different color before. Whoops, that's not what I want. So we'll say it was yellow. And I'm going to add base. That's what was there before. Okay. So we're going to say I have 25 milliliters of an unknown concentration of this acid. So I'm going to use a titration to figure this out. So we open up the valve and drain it out. And when it gets to here, this solution now goes green. Green is pretty much the indicator. Well, that's a dumb word to choose, but it's the thing that indicates that it's neutral most of the time. Well, it's not. It's, I was gonna say, it's the indicator of whether it's an acid or a base. But it's dumb to describe an indicator with the word indicator. That's all. Okay, so once it turns green, I can keep track of this information, and usually it's pretty simple. Because remember, when something's neutral, the moles, H plus, are equal to the moles, OH minus. That's what neutral means, right? Okay, now look right here. I have a concentration and a volume. When I multiply those, that gives me the moles, right? So I can say that this is the OH side. I can say 2 times 30 is equal to, this won't matter. If I keep them both the same, it won't matter. Because then the answer will just tell me the milliliters to add. If I did it the other way, it'd tell me the liters, which is fine either way. All right, so I have 2 times 30 equals 25 times something I don't know.
Oh, so then you just divide by,
Yeah, you multiply the pair, and divide by the loner. Algebra, 12/5. What's that? And that's all you would do. It is fairly simple to do those parts. Yes, Judah.
Is there strong bases and strong acids that put together will turn neutral faster? So like what you do with strong fluid?
Well, it really depends on the concentration on how fast it goes. But yes, strong bases and strong acids make perfectly neutral. Weak acids and strong bases, or weak bases and strong acids, they will be either a little bit more acidic or a little bit more basic. Yeah, and we're going to talk about that probably in the next couple slides. So far, sort of okay? All right. All right, so this is where they get a little bit more tricky, because it wants us to now calculate the pH, which we can do. Let's just go through this together. A 20 milliliter sample of 0.2 molar HBr solution is titrated with that much NaOH. Calculate the pH of the solution after the following volumes of base have been added. So if I know we've been doing buffers forever. This is not a buffer problem. This is a titration problem. It's a pH problem. So if I need pH, ultimately pH is equal to the negative log of the H plus concentration. So what do I need to do on all of these? I need to find the H plus concentration, or the OH, and then I can take POH and subtract it. So this is the ultimate goal here. So we have, yep. Okay, so first thing first, who's our best friend? Cooper Lloyd? Moles. So I need to know how many moles of HBr. I have 20 milliliters, which is really 0.02 liters. And I know I just said you don't need to do this, but we're ultimately finding the moles divided by the volume for concentration, right? This is not just a standard titration problem. All right, times 0.2 equals 0.002, doesn't it? Oh yeah, 4. I just wrote a 4. Okay. So, and that's moles of H plus. And yes, I know, Mr. Davidson, there's a BR. I know, I don't care. No, this is a strong one. That's why I don't care at all. That you're not supposed to admit that you looked it up. Okay. Now, every one of these problems, I'm adding NaOH to. So this is strong and strong. So there's no hard, there's no buffer. There's no Ka necessary. This is just straight strong acid, strong base, just find the excess and negative log it. Okay, so this is what I have in every problem. So A, it wants the addition of 15 milliliters of 0.2. So I'm going to calculate the moles of OH from those two numbers. So I have, did I say 15, right? Why have I lost where that number is? Oh, it's right here. I'm looking way up here. Okay, so I'm going to take 0.015 times it by 0.02 again. 0.2. All right. And this is 0.003, right? So 0.003 moles of OH minus. Okay. Every one of these problems, you'll do it the same way. You convert to moles, and then you find which one of the things is in excess. So between the H plus and the OH for part A, which thing's in excess? H plus. And how much excess is there? All right.
Oh, because you should bigger, subtract smaller.
Yep. 0.001 moles of H plus. Now, I'm close to what I ultimately need, but what do I need? What do these brackets mean? Concentration. So I must divide by the total volume of those two things added together. Yep. And what does that give me? 0.035 is the 20 milliliters plus the 15 milliliters. That came from subtracting the moles of H plus I was given minus the moles of OH, because the smaller value will react with the larger value to make water, and it will leave whatever's excess, H plus or OH minus, it will leave that. All right. Anyone? Yeah. Yep. And it's, well, you have to change them both. This is the only thing that does not change. This stays the same forever in every problem. All right, so this answer to this piece is what?
Would you put it in the negative log after all?
Oh, you will, but what is it?
0.029.
It's got to be smaller than that. No, never mind, you're right. 0.029, we agree? Okay, now that's the concentration of H plus. So then we negative log it. So the answer to A is that the pH is equal to the negative log of 0.029. I plug that in and I get some number. All right, 1.5, what? 4, good enough. Okay, now that's pretty acidic, and that's justified. Anytime you have pure H plus in excess, you're gonna have a pretty acidic substance. Well, if this problem gave you something that wasn't, then you'd have a buffer and you do the math completely different.
Titration will always have a stronger.
Math-wise, 99.5% of the time. That's what that 99.5 was on that previous slide. Okay. This acid would burn, but not that bad. Say it again, you're right. Yep, C is just 7. Why? Okay, equal moles of acid and base there. All right, I will do B, you can do yourself. Let's look at D together. I'm skipping to D. All right, so I'm gonna erase all this stuff. All right, so letter D, we now need to know, we still have 0.004 moles of H plus, that's a constant. In D though, we have 0.0201 times 0.2, that is Is it that 0.00402? Why am I doubting myself? I don't know. All right, and that's the moles of what? OH minus. Okay,
Well, sometimes they give us the constant of the OH,
yeah.
like we just put that.
Mhm. Okay, so we'll have excess now. So we take the big number always and subtract. I know it's ugly, but we're going to subtract upwards. And we end up with the difference of what? 0.00002. Is that right?
Yeah.
Yeah, that's moles of OH minus. You can, yeah, you can put a scientific notation. Okay, but I have to divide that by something now, right? What do I divide it by? Point. 0.0401 liters. Where did that number come from?
The total.
Okay, that's the sum of both volumes, right here and right here. Okay, then I get some number which is equal to what? Okay, we'll call that good. Okay, and I'm going to rewrite this in a different way. I'm going to say this. I'm going to say that pH equals 14 minus the negative log of this thing.
Oh, because that would be your POA.
Right, because we're going to find the POH. So we got to make sure, remember to subtract 14 from it. And anyone have me an answer? Sounds good to me. Okay, now, does that number make sense? Yeah, we're just barely in excess of a base. So it is basic. It's not super basic like a 14 yet, but there we go. If we do 35, we'd end up with a pretty close, probably like a 13.2. All right.
Wait, so on the AP chemistry test, I know that the AP calculus is like this, but if you just get number and like, if you just were to write the, not the final answer, but I'm gonna simplify it with this one, you just will count 20.
But you didn't put the answer, you would not get full points. This problem would be probably worth 3 total points, 2 for the value. They'd probably say that this is my guess. They'd say 1 point is earned for the calculation of the moles of H plus. 1 point is earned for the calculations, and 1 point is earned for the right answer. What's the ACT? Science. I think it's 60 questions. I should remember, but they changed it last year and now my mind doesn't remember. They didn't change it permanently though. Judah.
That's from subtracting.
Right here. 40. That sounds right. Thank you. This is how much H plus we have. This is how much OH minus we have. We subtract the small number from the big number. If you take 0.00402 and subtract 0.004, you end up with that. What? All right, so here we go. Titration math. It's not intended to be hard. but I know, like, there's 20 million ways to do math on AP Chem. I'm aware of that. So it's not that any of them are hard, it's that all of them together are hard. So you use chemistry and math to determine the excess H plus or the OH minus. That's all you have to do. And then you negative log it. Now it's easy for me to say that's all you have to do, but you find moles of each, find which one you have excess of, and negative log it. If you find POH, remember to subtract from 14. Okay. We did not, we're going to keep going, but I forgot titration. I thought we went straight to KSP. Watch there be something more. Oh, sweet. Titration curves. All right, you should recognize the shape of a titration curve. It's a lot like exo and endothermic shape-wise. All right, let's see. Whoops, I meant to do that. Is there another one? Okay, whatever. We'll draw one here. So what they'll have is they'll have pH, and usually it's versus the volume added. That says volume, not Venmo. All right. I don't know. Ask Derek. He always gets money from it. A titration curve will look like that, or it can look like this. Whoops, that's too sharp. I was doing equilibrium for a minute. Now, I know you think, well, that's the same as an equilibrium, but you wouldn't have both at the same time. I'm just saying they can start higher and low, or they can start lower and high. So the first thing you should know is what this is. This is a titration where we are adding base. I'm starting with an acid, and I'm going to titrate it with a base. And honestly, I should write the word strong here. We can recognize this shape as a titration curve where a strong acid is being titrated with a strong base. The way I know it's strong, and don't draw this over the top either, is that this line is almost flat and that line. If it's weak, this line is a lot more like this, and it's a lot more like that. So the changes are more gradual than here and then there. Because even my black line, it's not really to scale. It's almost like straight up. But anyway, okay. Then the other one, go ahead. The volume is the volume of base added. So remember this picture? Where'd it go? It's how much of this I'm adding. You with me on that? Okay. Okay. Now, at a pH of 7, we'll pretend that's 7. We get this point right here, and it has a name. It's called the equivalence point. Now, there's a ton of different places where equivalence points are that you will learn in college. But for us, we really just need to worry that it's where a pH of 7 is. The equivalent point is where the OH moles is equal to the H plus moles. And you should know what's happening here.
Water.
And you know, it's not water. This would be water. And you should know what's happening here. All right, good. At these points here, we have excess acid. Nope. That has absolutely nothing to do with it. And here you have excess OH minus. What? Equivalence. I'm sorry. I can't live without scratching my back right now. Oh,
Hey, no,
oh, that feels good. I'm not that flexible. It was too high. I could tell. One time I used a pen in church to do that, and this lady leans forward. She's like, "You just drew on your shirt." Oh, that.
That is really embarrassing.
It was pretty dumb. All right. Now, if we were looking at an indicator, we'll just pretend it's bromothymol blue. It'd be yellow. Okay, then it would start to gradually turn grello. I know that's not grello. And then it would go blue. And this can change with literally one drop. This is a vertical line pretty much.
I forgot, those the primary colors or right up primary colors?
Oh my gosh.
Are you serious, Cooper?
I don't know.
No, like really. I know.
I don't know.
Are you-
I'm singing the primary song.
Colors,
The primary colors are blue, red, and yellow.
Red, yellow, red.
The secondary
Red, yellow,
colors
red. Exactly.
are.
Okay. Hopefully you drew that out and labeled it. Did you draw it out and label it?
Yeah.
Okay. They'll expect you to know what's happening at each time. All right. So titration of strong acid and strong base from the start. pH starts to rise just barely, and then it goes almost straight up, and then you go flat. Now, the exact same thing works if we do it the other direction. Let's see here. That was more work than it needed to be. The base would slowly change, then it become very acidic, and then it'd go flat. Okay.
If it's the other way, the bottom is going to be volume of strong acid.
Yep, it would be acid.
Ever have
The pH is just the standard we always use. I mean, we could say it, but it doesn't usually ask for that. What?
Oh, would that be with a weak base?
This one? No, it's still pretty slow. If it was weak, it'd be a lot more like so, but it is a little more slanted than the rest of them. All right, so just before and after the equivalence point, the pH increases rapidly, like vertically. We go from a pH of around 2.5 to, I don't know, 11 point something with almost no addition of base.
Like how fast are we going?
Well, remind me tomorrow, well, we don't have beat time, and I'll set it up, and you'll notice it's like 3 or 4 drops. It can go from yellow to a blue. All right. At the equivalence point, I already said this, moles acid equals moles base, and the solution contains only water and the salt from the cation of the base and the anion of the acid. So if you do this with NaOH and HCl, you end up with NaCl aqueous, just salt water, and then just water. All right, whatever. We'll pick this up tomorrow. We only have one thing left, I promise. It's not bad. There's math. There's always math.